The hour angle, which we will refer to as HA, is yet another angle used to measure position of objects in the sky, and this would be part of a local coordinate system. In other words, this angle is fixed for a given observer, and the grid that would represent the various hour angles does not move relative to the observer. Remember that for right ascension and declinations, which are coordinates fixed with the celestial sphere, those right ascension and declinations move with respect to the observer, since the celestial sphere itself moves with respect to the observer. So again, the hour angle does not move relative to the observer. So let's draw a celestial sphere with an observer located in the northern hemisphere. And let's take some arbitrary angle here. So this is your NCP, and here is the SCP. So the first thing we need to know is, to remember, is our local meridian, which goes north to south along the highest meridian here, so through the zenith. So on this side is south, over here is east, and now there is west. Now, the hour angle, which is measured in hours from 0 degree to 360 degree as an angle, corresponds in hours to a value from 0 hour to 24 hour for a full turn. Now, this coordinate system, this hour angle system, is aligned with your polar axis, with the NCP to SCP axis, and the various circles that go from the NCP to the SCP all around your celestial sphere will represent the various values of our angle. So if we go from the NCP and we go straight up along the local meridian line all the way to the zenith, and then continue all the way to the SCP, we have what looks like a great meridian, and this meridian here is 0 hour angle. So the 0 hour angle goes through your zenith and connects the NCP to the SCP. Now, if we imagine 24 circles or semicircles that run parallel to this line, so therefore they will all run from NCP to SCP, just like the meridians do on Earth, all of these meridians would separate the grid into 24 quadrants, and each one of them would be separated by 1 hour. So these are the hour angle. Now, you think that the right ascension does something very similar. And I'll take a moment here to remind you what is the right ascension. The right ascension is a coordinate system fixed with the celestial sphere. So you would, for example, have a right ascension of 7 hours somewhere here, 7 hour right ascension. And this is in front of the page as I'm drawing it as a solid line. If I go towards the east, I would increase my right ascension. So that would be 8 hour right ascension, over here 6 hour right ascension. And as the celestial sphere rotates around the NCP from east to west, the right ascensions itself rotates in the celestial sphere. So 1 hour from now, the stars that are over here will come over here. So the stars that have a right ascension of 9 hour will be at the position right now occupied by the 8 hour right ascension stars. And the 8 hour right ascension stars, 1 hour from now, will occupy the same position as the 7 hour right ascension stars. Okay, so right ascension, which is also separates the celestial sphere in 24 slices like this, rotates. Meanwhile, the hour angle system does not rotate relative to you. So the 0 hour angle, which is defined from NCP to SCP, going through the zenith and therefore aligns itself with your local meridian, well, this 0 hour will always remain 0 hour. So over the course of the night, as the stars rotate, all the stars will transit, will do the transiting. And when they transit, they will all cross the 0 hour angle when they do their high transit. So 1 hour after they transit, they will cross the next meridian here, which will be defined as the 1 hour angle. So think about it this way. If a star that is transiting crosses the 0 hour angle, then 1 hour after it transits, it will cross the 1 hour angle. 2 hours after it transits, it will cross the 2 hour angle. 5 hours after it transits, it will cross the 5 hour angle. So, with this logic, what hour angle corresponds to the line that goes from NCP to SCP but goes through the opposite side of the zenith? Well, you guessed right, that's the 12 hour angle line. And a star that is transiting now will be on the opposite side 12 hours later, 12 sidereal hours later, which is not the same thing as 12 solar hours, right? Remember, a star will do a full turn around the sky in 23 hours and 56 minutes. So, these hour angles separate the sky in 24 segments, and a star would move from 1 hour angle to the next in 1 sidereal hour. So it's a little bit less than an actual hour in your clock, because sidereal time is a bit shorter than solar time. So let's see what is the difference between the hour angle and the right ascension using Skyview looking north. So let's take some arbitrary points in the northern hemisphere, so that at some point here we have the NCP. This is your local meridian, and the stars will appear to rotate around the NCP here. So the hour angle going from NCP, so we're looking north, this is east, this is west. The 0 hour angle starting north from NCP going straight up, this goes right overhead, circles around and lands in the south behind you. So this is the 0 hour angle. If I take the line going straight down, so a star transiting here would take 12 sidereal hours to reach this side. So this will be the 12 hour angle. And I can divide this up further into 24 pieces. So this would be going west, 6 hour angle. How do I know this is the 6 hour and not this one? Because I know the direction that the stars take around the NCP. And I know that stars would rise up from the east, rotate counterclockwise, looking north, and set near the west. So here like this, right? So I know that from 0 hour, it will take 6 hours to reach the 6 hour angles. Again, 6 sidereal hours, so a little bit less than 6 hours on your clock. I can divide this further into 1, 2, 3, 4, 5, 6. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I'll write 18H, 18 hour angle. So yeah, there's 2 H's in there. And then 18, and then 19, 20, 21, 22, 23, and 0. And of course, those circles, those lines are all supposed to be equally distant. So these lines that represent the hour angle, so this would be 1 hour, this would be 2 hour angle, are fixed. So over the course of the night, as the stars rotate, these are circumpolar stars that we are seeing here. But I can imagine a star that is rising near the east that is not circumpolar. These stars, all of them, go around and they transit at 0 hour angle, And then 6 hours later, they reach the 6 hours hour angle, and so on. Starting up, the hour angle increases towards the west. And this is the opposite direction of the right ascension. So if I pick any star with some random right ascension, so for example, this is my 0 hour right ascension, which corresponds to the vernal equinox point, then the 1 hour right ascension will be 15 degrees to the east. And the 2 hour right ascension would be this way. And the angle, the lines that correspond to the different hours of right ascension don't even have to line up with the hour angle, because they are turning, constantly turning. And at one point they will line up, and then they will move on and line up with the next one and move on. So this 0 hour right ascension point, well, you can imagine a bunch of stars here all rotating from east to west. A couple of hours from now, this meridian of right ascension will be here at the 0 hour hour angle. So the 0 hour right ascension will temporarily coincide with the 0 hour hour angle. And then we'll continue on, and 6 hours later, this 0 hour right ascension angle will be here. So the hour angle is attached to the celestial sphere, and the celestial sphere rotates. So the hour angles, the right ascension angles rotate, while the hour angle is attached to you and therefore does not rotate. So the hour angle increases towards the west, and the right ascension increases towards the east, increase in the opposite direction.